Hello, welcome everybody to this video podcast from Anritsu. My name is José Pindado and I am Field Application Engineer in Southern Europe. Today we're going to cover one of the most interesting topics in the spectrum analysis, that it's the mixing process in the spectrum analyzer, having a special focus on the difference between the harmonic mixing and the fundamental mixing. In the agenda, we will start with some fundamentals of a mixing process, a small overview of what the mixing process is, as an introduction to the difference between the fundamental mixing and the harmonic mixing. After that, we will have a small overview of the millimeter wave spectrum analysis portfolio in Anritsu. Finishing this presentation with some problem fields we can find in the field and some solution that Anritsu are proposing with his new fundamental mixer regarding some noise floor improvements, dynamic range improvements, better image response, etc. Fundamentals of mixing. When we are talking of mixing or frequency multiplication, what we are talking about? We are talking mainly on the distortion of a typical sinusoid, that it's an abrupt change in amplitude or time, that it's generating multiple output signals at higher frequency with lower amplitude. This distortion is usually realized with a characteristic of nonlinear semiconductors. Can be diodes, can be transistors of different types, etc. Of course, with all these multiple frequencies that we are getting at the output, we only want one of them, so the desired signal will be filtered for further processing. Okay, so when we just take a look of typical linear device, has typical linear transfer function, if we put at the input of this device just one sinusoid of a certain frequency, what we will get at the output is another sinusoid with exactly the same frequency component but with a different amplitude. This amplitude can be higher in case of an amplifier, or it can be lower if the device is an attenuator, is a filter or coupler, divider or whatever. But the behavior of this device should be linear. What happens if this device is nonlinear or has a nonlinear transfer function? In this case, for example, okay, this transfer function is completely theoretical. We have a linear behavior in the positive voltage of the signal. We have a very flat response that will cut off the signal in the negative part of the voltage. So what we will get at the output is something like what we see at the left of the slide. In the negative part of the voltage, we don't have anything. All this signal has been cut off. And in the positive part, we have the same sinusoid. But the signal itself has many frequency components at the output. Okay, this is just a very theoretical transfer function. But it's not much different what we can find in the reality. In this case, for example, this is typical diode behavior. So we can see that in the negative part of the voltage, we have the same flat response, so the signal will be cut off. And in the positive part, we have, instead of a linear behavior, we have some nonlinear behavior. So the signal at the end will have a lot of frequency components that, okay, we can take advantage of that for our use. So having in mind this behavior of nonlinear device, what do we want to do with this behavior? First of all, we want to characterize some characteristic of this nonlinear device. For example, we have at the output of these multipliers, we have one sinusoid with a certain frequency with an input power, And what we will get at the output is a bunch of different frequency components that we will only need one of them for our purposes. So this frequency that we will get from all this bunch of frequency components will be the output signal, let's say. This signal will always be the frequency, the input frequency signal multiplied by a certain factor. This multiplication factor is one of the main characteristics of our device. Then we also have the output power. In the previous slide, I said that this nonlinear device will usually give us a lot of frequency components, and all of them will be of lower output power. So this output power will be usually lower than the input power. So we'll have a conversion loss that will define also our device, our nonlinear device. And then if we use some kind of filtering at the end of our mixing process, okay, we can suppress somehow this undesired harmonics, these other frequency components that we don't want to use. So this is another characteristic of our nonlinear device. Okay, talking of mixing, we can talk of two different techniques. One of them is the additive mixing. In the additive mixing, we are using resistive network, for example, to just add two different signals to different frequency components, and then these two different signals we are feeding one nonlinear device just to create all this bunch of different frequency components at the output. Then at the output, what we are doing is just filtering this bunch of frequency just to get the frequency that we want to use. Okay. And then the other technique is what we call the multiplicative mixing. In this case, we are using a multiplicative device that will get two different signals and will multiply these signals, and at the output of the device we will have the result of this multiplication. Okay, so let's go for a kind of mathematic function. If we get the output of this nonlinear device, the output I have already said that it's the multiplication of these two sinusoids, this cosine. If we go to the basic of trigonometry, we can know that this multiplication can also be shown as the addition of these two cosines, having the frequency both cosines. One of them is the subtraction of both frequency and the other one is the addition of both frequency. So what we have at the output at the end is just two signals with two different frequencies, and these two different frequencies are made of the addition of and the subtraction of the LO frequency and the RF frequency. What we are doing at the end is just filtering these two frequencies just to get the one that we want to use. This is one of the typical architecture of this multiplicative mixing. We are using a typical diode bridge in which, depending on the positive voltage or negative voltage, one of the branches of this bridge will be used, and we can have both frequency and we can get the IF frequency at the end. One of the most common technologies used for these mixing devices is the Schottky-Diodes. A conventional Schottky-Diode will present a very abrupt amplitude cut in the input signal. It's this amplitude cut that will give us at the output a very rich in harmonics frequency response. So we'll have frequency response very high in frequency. In this case, we can have a spectrum up to 3 terahertz. But on the other hand, these Schottky diodes will usually require a very high input power of, let's say, between 1 and 10 watts. Typically, Schottky diodes will work in a single diode configuration or also in an anti-parallel configuration. And here we can see a typical Schottky-Diode mixing device where we can have radio frequency matching network and LO matching network, and in between we have the Schottky diodes in an anti-parallel configuration to get the IF response. Another technology is the linear to infinity element. And one of best examples of this technology is the step recovery diodes. This step recovery diodes presents a very abrupt transfer function, like the one we can see here at the left of the slide. And this transfer function will give us at the output of the device a signal that is much similar as a comp in time. This pulse train that we have at the output of the step recovery diode is a signal that is in the frequency domain, a signal very rich in harmonics also. So how is step recovery diode working? Okay, basically step recovery diode is a semiconductor junction diode, and it has the ability to generate extremely short pulses. Basically, it's working like a varactor or a charge storage diode. So when the diode is working in forward conduction, it starts storing the charge, and once it goes to the reverse conduction, it starts throwing all this charge that has been already stored. But it starts throwing all this charge with presenting a very low impedance. But after all this charge has already thrown, suddenly this impedance turns into a very high impedance. This abruptness will characterize this step recovery diode by giving us these very short pulses. As multipliers, these step recovery diodes can have cutoff frequencies of some 100 gigahertz, like 200 or 300 gigahertz. And the pulse generation up to 100 picoseconds is feasible. Okay, now we are done with the principles of mixing. Let's go on with the differences between fundamental mixing versus harmonic mixing. Harmonic mixing has been since years the preferred technology for spectrum analyzers, mainly due to cost and also simplicity of the technology. Okay, if we take a look at the mixer stage in a spectrum analyzer, the main goal of this stage is to down-convert the RF signal into the appropriate IF signal, so this signal can be analyzed and post-processed by our instrument. This IF signal will be the subtraction of the RF minus the LO, or the LO minus the RF. So if we get a high radio frequency signal, this LO signal will also need to be high. And this is a real challenge because it's not easy to manufacture a local oscillator that is high in frequency, high quality, but also low cost. So we will need to find a different solution to try to analyze high signal. And that's where harmonic mixing technology comes into play. In harmonic mixing technology, instead of using the fundamental frequency of the local oscillator, we will use one of the harmonics of this local oscillator. So to get the appropriate IF, we will try to reach the radio frequency signal by means of using one local oscillator and one of the harmonics. In the case of the Anritsu benchtop spectrum analyzer, the IF will be constant and will be 1.875 GHz. This is the case of the MS2830, 2840 and 2850. This is the way of reaching high frequencies. So in the worst case, in which we will work with the second harmonic, for example, local oscillator frequency should be not higher as half of the radio frequency. If we are trying to get higher in frequency and we are using higher harmonics, local oscillator frequency can be even lower. And this is one of the main advantages that we have in harmonic mixing method. Let's put an example. Let's consider we are trying to analyze a 60.5 GHz signal. the instrument we are going to use is one of the Anritsu benchtop spectrum analyzer, which is using an IF of 1.875 GHz. Considering the local oscillator frequency can sweep from 5 GHz up to 10 GHz, we need to find the appropriate LO frequency and the appropriate harmonic number to combine with the 60.5 GHz and reach the IF, the appropriate IF. In this case, we are using a frequency of 6.328 GHz for the local oscillator, and we will use the 8th harmonic. If you make the numbers, we can see that we can get the appropriate IF to be analyzed, and hence we can analyze the signal. Here in this graph, we can see one of the main disadvantages that we will have, and that is that the higher the order, the lower the output power we will get in the local oscillator. This will highly impact in the dynamic range. So which are the advantages and disadvantages of this harmonic mixing method? Well, first of all is the LO frequency can be moderate low. Okay, in the worst case, we will require only half of the radio frequency. So this local oscillator source will be much easier in realization and also in cost. We will also have high rejection of VLO leakage. And as a third advantage, I would say that these devices can be moderate cheap in cost. But we will also have some disadvantages of this method. First of all is conversion loss. That is several orders of magnitude higher than the conversion loss of the fundamental mixing. To try to compensate this, we will also need a higher LO power. And then lastly, we will have inherently narrower bandwidth and also a slightly lower 1 dB compression point and third order interception point. Okay, let's go to the same example, but now with a fundamental mixing method. We are trying to analyze again the 60.5 GHz signal using the same Anritsu benchtop spectrum analyzer. So the IF is exactly the same. The local oscillator will sweep again from 5 GHz up to 10 GHz, but now we are not using a harmonic mixer anymore, we are using a fundamental mixer anymore. That means that the local oscillator frequency will be that combined with the RF signal will give us the appropriate IF, the 1.875 GHz. So the local oscillator signal will be 58.625 GHz. How do we get to this local oscillator signal? Well, the mixer inside, the fundamental mixer will multiply this local oscillator frequency to get to the appropriate frequency to be combined with the RF. In this case, the power is higher, we'll have less conversion loss and the dynamic range will be improved. Of course, some further filtering will be needed. So the advantages of fundamental mixing is basically a lower conversion loss. So the driving local oscillator power output, instead of being quite high, is, let's say, moderate high for convenient frequency designs. And this will reduce the conversion loss and will minimize the DANL, the degradation, the noise level degradation. Of course, we will have also, we will avoid the generation of unnecessary mixer response. It will be easier to identify unwanted mixer response because we are only driving one LO signal. In the case of harmonic mixing, the signal under test will be mixed with all harmonics that will contribute to unwanted response. So on this background, the fundamental mixer has an inherent advantage. Okay, now we have already seen the differences between harmonic mixing and fundamental mixing. Let's have a small look at the millimeter wave spectrum analysis portfolio overview in Anritsu. Anritsu is offering a fundamental mixer that has a very large dynamic range, very wide measurement span. It's a very simple connection because it's using only one cable in which the LO, both the LO and the IF is traveling. And we can have a conversion loss table in a US memory that can be loaded in the spectrum analyzer. So all this conversion loss can be subtracted from the measurement. We have two units that is covering the V band between 50 and 70 gigahertz, and also the E band between 60 and 90 gigahertz. The first one focused mainly for WiGig and wireless backhauling, and the second one can cover all car radar manufacturers and also wireless backhaul. If we take a look to a small comparison between the behavior of the high performance fundamental mixer against the harmonic mixer, we can see that we both covers the E band, for example, in this case. But if we take a look to the conversion loss, we can see that the fundamental mixer has 20 dB better conversion loss. Also, the 1 dB compression point is much better in the fundamental mixer. And last, the DANL has a better performance also in the fundamental mixer. So this will give us a much better behavior in the fundamental mixer rather than in the harmonic mixer. This is quite important in some measurements that are critical for example, radio link manufacturers and so on. So as a summary, we can highlight that we have a DANL of minus 150 dBm normalized per hertz at 75 gigahertz. So we are capable to measure very small signal levels like harmonics, spurs, and so on. It is an optimized mixer designed to minimize the conversion loss without additional need of noise cancellation methods. Noise cancellation methods that we also have in our spectrum analyzer. With a higher measurement speed compared to these noise cancellation method based instruments, very good 1 dB compression point performance above 0 dBm, so it is capable to operate with high input levels, and it is ideal for spurious emission measurement or spectrum emission mask measurements. Now, in this final section, we are talking about some problems we can find on the field and the solution proposals Anritsu are making with his high-performance fundamental mixer. Until now, when evaluating the transmission characteristics of millimeter wave wireless equipments, it requires the combined use of a spectrum analyzer and harmonic mixer. And this causes several fundamental problems. First one, we should talk about the poor minimum sensitivity, low dynamic range, high conversion loss that will affect to mainly emission mask measurements. Second problem is the appearance of image responses in the measurement range. This is much related to the span requirements of the measurement. And then we can also talk of phase noise contribution of our harmonic mixer. Okay, let's talk first of all of the minimum sensitivity performance, poor minimum sensitivity performance of the harmonic mixer and the conversion loss. It will affect mainly on the sensitivity for the over-the-air measurements when doing measurements or characterizing WiGig modules and so on. But it will also affect also to the spectrum mask measurements of wireless backhaul outdoor units. This large conversion loss or low dynamic range of the harmonic mixers make it impossible to ensure margin enough to match the measurement standards. For example, this standard that defines the spectrum mask of the E-band backhaul outdoor units. So, to try to solve this problem, we need to look forward for a solution with very low conversion loss, ideally lower than 10 dB, and with a very low DANL, very good sensitivity in terms of noise. So let's put an example. Talking again with this standard that is defining the unified band spectrum mask. This standard is defining that the offset frequency F4, that means this frequency, should be 45 dB below the main carrier, that it's this level. This is for a channel separation of 1 GHz, that means a channel bandwidth of 1 GHz. So, in line with 1 dB compression point, existing spectrum analyzer with external mixers, harmonic mixers, do not comply to this standard. The huge dynamic range requirement is really hard to fulfill with existing technology. But in the case of high performance fundamental mixer of Anritsu, we can ensure that for a channel separation of 1 GHz, we can meet even 50 dB for this frequency offset. And for the channel separation of 2 GHz, we can meet the 47 dBs for this frequency offset. So we can see that we need a very high performance mixer to fulfill the requirements of this standard. This is just a comparison of we can reach with a harmonic mixer solution versus the fundamental mixer solution. Harmonic mixer solution with 1 dB compression point of -7 dBm, DANL of -115, normalized to 1 Hz. So DANL performance is not that good. We have also some flatness problems. We can see that measurements of spectrum emission mask cannot be achieved with this solution. On the opposite side, if we use a fundamental mixer solution with a very good 1 dB compression point above 0 dBm, a very good DANL of -150, we can see that the dynamic range, the margin that we have is really good, so we can approach this kind of measurements. Of course, we can also use useful tools like noise floor reduction and so on that we will help to improve this kind of measurements. Problem number 2 is the appearance of image responses in measurement range. When doing measurements in the millimeter wave band, we are not using a preselector in our spectrum analyzer. We are using a mixer, and measurements using a mixer suffer from the appearance of signal at about same level but different frequency from the actual input signal. When down converting a millimeter wave signal, both the true signal and image responses are down converted at 2 locations where the frequency of the local oscillator complies with this formula, causing image responses at frequency of twice the IF frequency from the input signal. This is something I already mentioned a few slides before. This IF will highly impact in the image response behavior of our instrument. In this case, the higher the IF, the better behavior of our spectrum analyzer. So it's not that good having a very low IF in the spectrum analyzer. Of course, we can also improve the behavior of our spectrum analyzer by means of different functions like signal ID and polarity swap. Let's go for a particular example. In this case, same example as in problem number 1. This ETSI standard is defining a specific measurement span for spectral emission mass measurement. In this case, it defines plus and minus 2 GHz span for a channel separation of 1 GHz and plus and minus 3.5 GHz for a channel separation of 2 GHz. If we take a look to this table, we can see that there is no existing solution composed by a spectrum analyzer plus harmonic mixer that is able to sweep such wide frequency span because the image response occurs due to the very low IF frequency of a signal. Only Anritsu MS2830 is able to sweep up to 3.75 GHz span without any image response due to the high IF frequency. And we can even double this span up to 7.5 GHz if we use one of these functions already mentioned in the previous slide. So how does this function works for increasing and improving our image response in our spectrum analyzer. What we do is just two sweeps using the positive polarity in our local oscillator and negative polarity in our local oscillator and comparing both sweeps. In the first sweep, we will have our real signal and the image response in the lower side of the spectrum. And in the second sweep, we will have again our real signal, and then the image response will be changed to the opposite side of the spectrum. So by means of comparing both sweeps, we can decide and we can get only the real signal and get rid of our image response. And then we can double this span free of image. And then we have the last problem, that is the phase noise contribution. In this case, as you might know, the phase noise contribution of a mixer, of a harmonic mixers, has pretty much to do with the harmonic number that it's using. Exactly, this contribution is 20 times logarithm of the harmonic order of the harmonic mixer. So far, the fundamental mixer is using the fundamental frequency of the local oscillator. We can get rid of this contribution, and the phase noise contribution is much lower in our fundamental mixer. We are talking of a phase noise better than -100 dB per carrier and per hertz in the 79 gigahertz frequency band, with an offset of 10 kilohertz or even 100 kilohertz. That means quite a flat behavior. So that is quite impressive if we compare to the typical harmonic mixer. And this is pretty much what I wanted to tell you in this video podcast. I hope you have enjoyed this video podcast. You have learned quite a lot and it's quite useful for you. And see you in the next video podcast from Anritsu. Thank you very much, everybody.